Well, hello, friends. It's a very exciting time of year. The 2025 AP Statistics questions were just released, and I'm going to share with you approaches and teaching tips for a few of the questions from that exam through the lens of the Desmos calculator, which just released a new fantastic suite of statistical tools. So let's dive right in. The first question we're going to look at today is question 3. This was the probability question about a restaurant, and they have a streaming service where they play songs. We're going to look at parts B and C, which is the meat and potatoes of this question, for where in every 1 hour period, 20 songs we played, and Miss Fay is interested in how many rock songs we played in a typical 1 hour period. And we hope that our students would identify that this is a binomial setting. If we look at the information given, we can see that 10% of the songs altogether are rock songs. And there is some important information here that any song can be replayed at any time. So we're ensuring the independence and that 10% is consistent throughout the problem. So let's take a look at how we can handle a binomial setting using Desmos and also use it to have students investigate the binomial distribution. So I have my calculator all set to go here. I have it in projector mode here. If you don't know how to do that, by the way, under the wrench, I'm just in the capital A mode here. We used to call it projector mode. So let's dive right in. So we're going to type in binomial dist, and the letters all stand up, which is good news. That causes us to think that we're doing this right. And parentheses here. Notice that we are given prompts for trials and success probability. We are doing 20 trials. The success probability here is 10%, 0.1. And you can see here that it seems like my distribution is starting to form. It's not very satisfying. I'd really like to zoom to see this better, but Desmos has us covered. We have the spyglass that I like to call it. We're zoom fit here. Click that and whoop, there is our binomial distribution. And you can click on any of these to look at their individual probabilities. The probability we would have 0 rock songs apparently is 12%. 1 rock song, 2 rock songs, 3 rock songs, all the way to 20 rock songs, which apparently is essentially 0. There's a lot of essentially 0 probabilities here. So let's take a look at this a little bit deeper here. We want to know what is the expected value for the random variable in part B. Okay, well, in order to find the mean here, now we certainly hope that students will do n times p and come up with the answer of 2. But if we wanted to actually find that mean, we're going to give this distribution a name. I'm just going to call it S for songs, S equals. And now that I call it S, I can do mathematical functions with this. I can now find the mean of S if I like, which is 2. I can also find the standard deviation of S, which apparently is 1.34. And again, we hope students will know the formulas and they're given to us on the exam, but we can also find these things by using commands for them. In part C, we want to find the probability that 4 or more of the rock songs in a particular 1 hour period would be played. So in a binomial distribution here, I want to find 4 or more. So it would be the sum of all of these individual probabilities. But here at the top, I see cumulative probability. Let's see what we have here. I can find an inner probability between values, outer if I like, left or right. And right is what we want here. X is greater than or equal to 4. And I see that that probability is 0.133. So we can use binomial dist here to find binomial distributions and their probabilities. You can also do this with normal distribution. And actually, let's take a peek here. We have under the plus sign here, under inference, we can add a distribution. I actually have some choices here. I chose a normal distribution, but we certainly could have picked binomial distribution or t distribution or chi-squared. So I encourage you to play around with some of those other distributions and think about how you could use those in your class. Okay, let's do one little investigative piece here too. Let's say we're learning about the binomial distribution in our class and we want to understand the shape and what the effect of the parameters are. Well, this 0.1 here is very interesting to me. What happens when we make that any value between 0 and 1? So we can get rid of the 0.1. Let's say we make it A, and that invites us to make it a slider. Would I like a slider? Yes, I like sliders. And now we have this slider that defaults to 0.5, and I can investigate the influence of that probability on the shape of the binomial distribution. And we can just let it play too and have some fun with it. Kind of looks like an old school calliope. I guess I'm aging myself with that word. So let students investigate this. You could also do this with the 20. You could change the sample sizes and investigate what happens when n times p is greater than or equal to 10. And when does it appear that a binomial distribution starts to appear reasonably somewhat like a normal distribution. So that was question 3 from last year's exam. Okay, now let's take a look at question 4. This is the 2025 inference question. We're never surprised when we have an inference question where students need to complete all of the steps here. This one, if you look, we are told that 22% of high school students in County W use an app. The teacher here, Karen, believes that the proportion of students at her high school who use the app to help them with their homework at least once per week is greater than the proportion for her country. So she takes a random sample, 130 students. 38 of the sampled students use the app with homework. So I hope you identify this is a one sample Z-test for population proportion. We hope that the students do that as well. And is there convincing statistical evidence at the 5% level to support Karen's belief? So we're going to do one sample Z-test for population proportion. Okay, let's see how Desmos can allow us to do inference now. Under the plus sign, add item, you might notice we have our new inference widget here that we can press and see what happens here. So we have different choices here. We can add a test for quantitative data, a Z-test or a T-test. I invite you to play around with those and see what happens if you try to do a 2-sample T-test and how you can put the information in. Spoiler alert, you can put in summary statistics or you can put in actual lists by typing them in. But here we have a Z-test for proportions. So let's do our Z-test for proportions. We have one sample. So number of successes is 38 out of 130. Do want you to note here, I would have the opportunity to do a second sample here and do a 2-sample test if I wanted to. But this is one sample. Let's create the test, see what happens. And I have some choices here, confidence interval or significance test. Now, certainly we're doing a significance test here, but while we're here, let's take a look at the confidence interval. If I needed it, I could get the 95% confidence interval. I see the 2 endpoints here, and I can even change this level if I like to be maybe a 90% confidence interval and explore what happens to the width of the confidence interval with different confidence levels. But here we're doing a significance test. Let's take a peek here. Here's a significance test. Our null hypothesis here, to go back to the question, is 0.22. And we believe that the proportion of students using the app is higher in our particular area. So we want a right-tailed test. And we can see that we have a p-value there of 0.023. So there's all the information students would need to answer the question. Certainly they need to go through all the conditions and be able to write a conclusion. We're never going to forget those big landmarks that we have to think about with inference testing. But there's some other things here worth looking at. Whenever we see 3 dots, that's a place we might want to investigate something. So here, 3 dots, I can export the significance diagram. Let's go ahead and do that. Oh, there it is. So here's our nice Z-curve, our normal curve here that portrays the actual area as a Z-score of 0.023. So we can get that drawing out of there if we need it. Let's look at one other thing here. I want to go back to the confidence interval. Just like in the last part, in the last question, it's always fun to play with sliders and see what happens to generalize things. Under confidence level, let's make that an A. Let's see what happens. Add a slider for A. Oh, it's down here. My significance level, my confidence level can be between 0 and 1. Watch what happens with that interval as I go down to now 0.75. We're kind of pushing the boundaries of what we'd want for a confidence level here. But we can go up towards 99% perhaps. And we can go down if we wanted to have, kids always want to know, can you have a small confidence level? Sure, you can have a 17% confidence level if you want. It's probably not going to be realistic to use that, but we can see the effects of changing the confidence level on the interval. So use that with your students and leverage that idea of when does the interval get wider? When does it get more narrow? So that was this year's inference question. Okay, the final question we're going to look at from 2025 is question 5 here. And question 5 oftentimes has a mishmash of different ideas from the course here. And in this question, we're giving a probability distribution of the number of bedrooms in houses sampled in 2024. And Part A, Roman numeral 2, is the part I really want to look at here. What is the mean number of bedrooms for the sample of newly built houses in 2024? And show your work. It is important that students show the procedure here. We're looking at expected value. We hope that students will take all values, multiply them by their probabilities, and add all of them. And please encourage your students to show all those steps. It's a little bit a bad idea when students don't show all that work, and unfortunately the readers need to ding them just for things that clearly the students knew how to do but just kind of missed on the details. But how can we look at a probability distribution here in the Desmos environment? Okay, we're going to look at lists here. You're going to find that lists are very powerful. So I'm going to make two lists. One for bedrooms. I'm going to call that B equals. And we use square braces to make lists. And I have number of bedrooms. 1, 2, 3, 4, 5. It goes up to 6, I believe. Yes, it does. And we also have the proportion. I'll call that P, capital P. Well, I just tend to use lists with capital letters. I think a lot of people do this. You don't need to, but it just kind of helps me separate lists from other values and parameters I might be using. And here I want my proportions. I have 0.12 and 0.22 and 0.28 and 0.22, 0.14 and comma 0.02. And I stop and look to make sure I have everything correct because that was a lot of decimals, right? Okay. At this point, here's a couple things we can do. We can simply define B times P, and notice I have this 6-element list, and if I give myself more real estate here, because I'd really like to see more, I'm going to drag this space between the two parts. And I can see those are all the contributions if I did B times P all the way down. And furthermore, I would like to know the total of B times P. So apparently our mean, our expected value is 3.1. So it's a great way to have students take a look at the probability distributions and to use the list in order to find values. Okay, so we went through 3 questions from the 2025 exam, but I also want to do one question as a bonus. This is from last year's exam. I believe this is question 5 from last year, where a data table was given here about types of baseball cards, and how long they've been collecting and whether they have rare cards and regular cards. And students were asked many different questions here, some probability questions. But the second half of the question asked students to name the procedure we could use to see if there is a relationship between how long someone has been collecting cards and the type of cards they might have. So now students in this particular question were not asked to do the full chi-squared test for association here. But I do want to show you how you can do this now, because it's very exciting how chi-squared is done with the new Desmos features. So let's go to our add item. Let's do inference. And we are going to do chi-squared for independence here. We want to see if there's a relationship between these two things. Okay, and notice we have a table that pops up here. So we can fill this table in, and I'm going to use tab to go from one space to the next. So my top group is 80 and 84. I'm going to tab over. I have 71, 76, and 112. Don't put in the totals. Some students will put in the totals. My second group is 11 and 16 and 9 and 6 and 35. And now I make sure I have everything typed in correctly. I believe I do. Everything looks good. Let's create the test. Let's see what happens here. All right, we have a lot going on here. We're going to need more real estate. So let's drag you over here. And first of all, let's take a look at the data observed and expected. So we have this table here that shows us observed counts and expected counts. And they're given in parentheses here. But let's see what else we have here. We can also look at the contributions. So notice how this is done here. So we get these little colored bars here, and we can see by inspection, visual inspection, that this group 5, group B, this is in the table. The people have been collecting for a long time, 21 or more months, and they have a majority of rare baseball cards. So that has the biggest contribution, and I can verify that. Notice that every cell in the table here has these arrows where I can look at more summary data. Observed, expected, and the contribution is 6.75. That's the contribution to the chi-squared statistic. And then this group 4, the contribution is 3.478. And these are much higher than some of the other contributions that we see here. There's 0.0042. And you notice that the observed and the expected are very close to each other. So we're not surprised that those particular cells don't add much to the overall chi-squared statistic. We also have a totals option here too, which will complete the scene, and we can verify that we have the table typed correctly. We can also do the significance test. Let's take a peek. Oh, here we have a p-value of 0.007, degrees of freedom is 4, the chi-squared statistic, and just like we did in the last test, we can export this curve as a significance diagram, and we can see it here. Let's bring my screen back here, and we can see this. And we have this 0.007, I think it's actually 0.00747 here. And students were given that value on the exam and were asked to reach a conclusion from it. But notice we can do the chi-squared test here if we would like to. And also notice that chi-squared distribution is now a command where we can find different things. I'll point out one other thing here too while I'm here. So we have the area here, and we found 0.07. Let's say I wanted to know where the critical value is. Where does the 5% area begin? So I can do bounds instead. Let's do bounds. And here I can type in 0.05. When does 0.05 begin? So apparently if my chi-squared statistic is above 9.488, I will get a p-value that is 0.05 or less. So notice the different things we can do here with distributions in terms of finding the area of regions and also going back and finding critical values. Well, so this was 3 questions from 2025 plus 1 bonus question. Hope you find them useful, and I hope you enjoy the new Desmos statistics tools.